All right, welcome back. So in the previous videos, we have considered a Schottky barrier when there is a metal semiconductor junction. We saw that the work function of the metal and the work function of semiconductor play a crucial role. We have considered an N-type semiconductor there. Okay? But you could also have a situation that you deposit a different material on a metal. Okay? For example, we could consider a situation where the work function of the metal, now here, work function of the metal is smaller than work function of the semiconductor. Remember, work function of semiconductor is simply the electron affinity plus the difference of Fermi level from the EC. So what happens if your work function of metal is lower? Okay. So in this case, there are higher energy electrons in the metal and they would actually enter into the semiconductor. This is how electron transfer happens, right? The other way it won't happen because the energy, there are actually the Fermi energy, the electrons in the semiconductor have smaller energy. They can't transfer into the other side, but opposite transfer happens. So when this happens, it's an N-type semiconductor and we are adding more electrons, right? We're increasing the concentration of electrons in the semiconductor. That's why you will see that in this case, the EF is constant, but then the bands are actually bending low downwards. So this point here indicates excess or additional electrons provided by my metal. Okay, so because of that you have additional charge and the metal will have the positive charge, so the electric field is going to be in the plus x direction. Okay, so what is happening here? This electric field also in some way is actually causing the electrons to accumulate at the interface. Okay, there is nothing like a depletion barrier now or depletion region. There's nothing like no depletion region. Okay, so in this case, no depletion region. So no barrier for current flow. You change the voltage and you will appropriate it. If you lower the EF, still current flows. If you increase it, also current flows. Okay. So this sort of a contact, between metal and semiconductor is known as an ohmic contact. Okay. So this is called ohmic contact. Okay. So why do we do this? Well, essentially, it's an important aspect of semiconductor fabrication. When you have semiconductors, we always want to make a contact with the external world, right? We can't simply deal with semiconductors alone. So we end up contacting a metal. When I mentioned the PN junctions, I mentioned this contact, right? So you're going to have another semiconductor device somewhere else. It's going to connect. All that is going to happen through metals. So the connection between metal and semiconductor is extremely important. Okay, and we saw that if your work function of the metal is higher than semiconductor, then we found that there is a rectifying contact that's happening. Okay, what do we mean by rectifying? You can draw the current voltage characteristics. So if you draw the current voltage characteristics, voltage versus current J, for a Schottky diode, it was exponential behavior like this, right? So what's happening is if you give a voltage which is, let's say a sinusoidal voltage, right? Whenever you give a negative voltage, right? For example, here, only reverse saturation current flows. Okay. Of course, there's going to be a small barrier, so it's going to be slightly positive. Till then, it's going to be only reverse saturation. Okay, sorry, I should not draw it here. Even here, right? Some above a certain barrier voltage, you can, above a certain threshold voltage, you will have current flowing. Okay, so in a way, this is called as a rectifying behavior. You are removing all the negative going parts of the waveform. Okay, that's why we call it a rectifying contact. And this happens whenever you have a Schottky barrier. So this is for phi m greater than phi s. Whereas you could also have what is called as a ohmic contact, wherein the current voltage relation is going to be like this. This is for ohmic contact. essentially telling you that the current voltage relation is given by Ohm's law, V equal to IR. This R is called as contact resistance. Okay. So whenever you make this contact with semiconductor and a metal, there's going to be some contact resistance. And that is going to be a significant feature when you actually make the contact smaller and smaller. Okay. All right. So yeah, this is a very important aspect experimentally. Whenever we fabricate, we do any research in semiconductor devices, we try to ensure that we evaluate the contact resistances and we make sure that the contacts are ohmic and not rectifying. Otherwise, the contact behavior is going to add up to your semiconductor behavior and it's going to complicate life, right? You can't study what happens at a junction if your contact itself is acting like a junction, right? Or a rectifying behavior. So this is for N-type semiconductors. We could also do the same analysis for P-type semiconductors, okay? Wherein, for example, if you have, let's say EC, EV, let's say there is a Fermi energy somewhere here, EF. Now what happens if I have a metal which is having EFM here? Okay, this is your metal Fermi energy. What happens in this case? You're taking a P-type here and a metal. In this scenario, of course, electrons are going to go from metal to semiconductor, electron transfer, right? So if you transfer electrons, what's happening to the holes? Because Fermi level is indicating the hole concentration, right? So we're in effect reducing the hole concentration, right? So in this case, again, you can draw the same band diagrams. No, I'll just draw a straight line, EF. Okay, this is going to be your metal. And closer to the in the semiconductor, you're going to have, okay, this is too wide, too much. Maybe I can draw something like this. Okay. So this is going to be your barrier height now, 5B0. Okay, why is it a barrier? Well, immediately you check. This is a gradient in the positive direction. So this is your electric field direction. So it is going to take your holes away from the junction. Okay. So your holes move away from junction, creating depletion region. So there is a built-in potential. And you have a barrier for electrons to holes to flow. Okay. So because of this, if your phi m in this case was, this is, if I take my reference level to be this guy, this is my phi m and this is my phi s. So phi m less than phi s implies rectifying. Okay. That's why we put this here. So this is exactly opposite, right? So this condition is opposite to N-type. In N-type semiconductor, phi m has to be less. Sorry. In N-type semiconductor, phi m has to be greater than phi s for forming a rectifying contact. In this case, phi m has to be less than phi s. Okay. So, and ohmic contact also same behavior. I would encourage you to actually see what happens when phi s is less than phi m and in a p-type material. Okay, draw the band diagram. That's a good exercise for you. The important point, I mean, one way I recollect, okay, this is a mnemonic that I use. Maybe it's useful to you or maybe not. So what I think is, whenever I have a semiconductor, okay, the work function of the metal has to be, for an N-type material, work function has to be here in the EC or above EC, okay? And in a P-type semiconductor, it has to be below EV. Only then I can form an ohmic contact, okay? So EFM above EC, EFM below EV for P-type. For N-type, it is above EC. Okay, so if EFM is above EC, essentially phi m is going to be less than phi s. Okay, so this is how I remember it. No, I don't, it depends, whether, of course, you can go through the actual electron transfer and analyze it. So whenever you have rectifying contact, you're going to have depletion regions. If you are removing majority carriers in the semiconductor, you're going to have rectifying contact. If you're adding majority carriers, you're going to have ohmic contact. Okay, and this has really a lot of significance practically because, as I mentioned already, you have these metal semiconductor junctions whenever you make a contact, and we want it to be ohmic. Okay, so sometimes we don't really have a choice. In this case, in the previous example here, what we end up doing is we actually dope it slightly higher, just below the contact. Okay, the reason we do that is, see, here are three different scenarios where the barrier is shown with an n-type semiconductor for different levels of doping: low doping, moderate, and high doping. Okay, so we already studied as the doping density increases, the depletion width reduces, right? So the depletion width was what? In this case, W is going to be, there was a 2 epsilon silicon. There should be a Q, I think it should be in the denominator, ND. Well, yeah, Q ND by epsilon silicon, right? Electric field. So, yeah, it will be correct. V built in. So, if you increase, increase in ND, decreases implies the width of the barrier decreases. And that is useful for us because if you have low doping here, you have a large barrier width and electrons have to cross this barrier and travel on the other side. Okay, thermionic emission process, right? But as you increase the doping, you see that the barrier width reduces. Once the barrier width reduces, here, like for example, if you take the high doping, it has become much smaller. So, quantum tunneling is much stronger. Okay, so even though there is a barrier, it still will conduct nicely. Okay, the resistance, contact resistance will reduce when you have high doping. Okay, so this is a very practical way where in the technology we tend to make ohmic contact. Okay, just dope it high just below the contact so that it always forms a ohmic contact. Okay, and there are also other practical considerations because the Fermi energy is not going to be so ideal like what you see. I mean, there's a lot of technological challenges that we have to address to make sure that the Fermi energy is actually changing. Okay, there are a lot more issues to that, but that will be a topic of a future, master's course. For now, I just want you to understand that Schottky contacts are important, and a practical way to actually make a ohmic contact is to simply, of course, choose an appropriate work function metal that works. But practically, it might be useful to simply dope just below the contact very highly. Okay, so that is a good way of making ohmic contacts. So with that, I would like to stop my discussion on the Schottky diodes, and we'll also post some assignments, from some gate question papers and all that. So please try to make sure that you understand. In this course, we are not really dealing with any circuits, so I'll encourage you to apply these concepts to the the questions, direct questions. It's not difficult. I mean, it's not elementary circuit theory is enough for you to understand and analyze that. So I'm sure you have already studied that. So you'll be able to answer the questions. Okay. All right. Thank you so much. I'll see you next time. Bye.